give a brief introduction to Adrian, who is today's speaker. He has kindly agreed to give today's talk. So Adrian is a professor in Applied Mathematics Department of University of Leeds. He received his PhD from DAMT, UK, from Cambridge. And then he went for postdoctoral position in Northwestern University in Cambridge. After that, he has been working at Leeds. So he has wide interest, mainly extrasolar planets, tidal interactions between planets and stars, astrophysical fluid dynamics, and instabilities and so on. So today he's going to talk about rotation and misaligned gravity, and connection with rotating mixing length theory. Okay, Adrian, all yours. So.
Okay, thanks for that. Yeah, thanks for the introduction. So do feel free to interrupt if you have questions at any stage. So I'm going to be talking today about work that I've been involved with for, well, I guess it started in about 2012 or so. So initially I started off working on looking at the properties of rotating convection in stars and planets when I was a postdoc at Northwestern. This is work with Adam Dempsey, who's a student there, and Joran Lidwick. And we had one paper published on this in 2014, so I've added the archive links to the two papers that I'm going to talk about today, but both of them have been published in journals. The second one was published in the Astrophysical Journal, and more recently, well, we started about 6 years ago, and then published the paper last year, was work with Laura Curry, Matt Browning, and Joram on the Misaligned case, which I'll talk about today as well. So that paper is also on the archive. And that paper was published in Monthly Notices of the Royal Astronomical Society. So I understand this is a turbulence audience and not as such a convection audience, so please interrupt if you have any questions about this, about the problem. So the motivation is that turbulent convection is influenced by rotation in many problems in astrophysics and geophysics, so in planets and stars. So in astrophysics, the structures of stars and planets are computed using often a simple theory to model convection called mixing-length theory, which is essentially a diffusion-free theory that has been very successful in modeling the key features of stars and planets, but the classical formulation neglects many effects, including rotation. So what I'm going to talk about is a simple theory that builds upon this, that describes the properties of rotating convection and how they're affected by rotation, which is important in many problems, not so much the structures of stars and planets, which are probably not going to change through this modification, but through affecting convective velocities and length scales, which have implications for mean flow generation in planets and stars, and in other problems, such as tidal interactions, which is a problem I'm very interested in. So on the bottom right, you can see a figure from a simulation of Jupiter's atmosphere, which shows the formation of zonal flows, which are generated through rotating turbulent convection in a spherical shell geometry. And this is one circumstance, so Jupiter's atmosphere, in which the fluid motions are strongly affected by rotation, and the turbulent convective fluid motions that are strongly influenced by rotation. And in the top panel, I've just showed a figure of the interior structure of the Sun, which shows the angular velocity contours. So red is indicating fast rotation, blue is, or the black symbol is slow rotation, and that is indicating that the solar convection zone is undergoing differential rotation, and that's the outer parts of the figure outside the dashed line is the convection zone of the Sun, and we know how fast it rotates from helioseismology. And this is a region which is turbulently convective and is affected by rotation, although to a lesser extent probably than in Jupiter and Saturn, which are more strongly influenced by rotation. So what I'm going to talk about today is looking at simulations and a simple theory to explore how rotationally constrained turbulent convection transports heat. And there's a simple predictive theory that we can use to explain scalings of bulk properties in rotating convection, which I'll compare with simulations. So the setup that I'm going to use is a standard dimensionless, a standard model to study convection is the Rayleigh-Benard setup. And so that's a setup where we have convection driven between a hot plate at the bottom and a cool plate at the top, separated by a distance, which are referred to as h here. And in this setup, the static conduction profile, where the heat is just transported through thermal conduction, gives you this linear profile in Z. where I've referred to n squared here is the square of the buoyancy frequency. So the temperature variable I've used here is strictly a buoyancy variable, which has units of an acceleration and not a temperature, but we're using what's called the Boussinesq approximation, which allows us to study the effect of convection in the simplest way. And the simplest variables I'm going to use is in terms of where the temperature, we refer to T as the temperature, but actually it has units of an acceleration. And the temperature gradient in this model is essentially has units of a frequency, really, and that's n squared, which is often referred to as the buoyancy frequency, which is the same buoyancy frequency that you'd have in a stably stratified fluid for determining the frequencies of gravity waves. So in a convective region, n squared is negative because we have hot fluid at the bottom, which is and hot cool fluid at the top. So n squared is negative. So this is the conduction profile here is this linear profile in Z, and theta I've referred to as the temperature perturbation about the conduction state. And so it's known from linear theory that this is unstable above a critical temperature difference, depending on the properties of the fluid. So above a critical Rayleigh number. So the Rayleigh number is this dimensionless parameter Ra at the bottom of the slide. I think I lost my pointer when I've gone to the slideshow, which is the a measure of the ratio of the buoyancy driving forces, which is related to the temperature gradient, ratio of that to the diffusive processes involving viscosity for the diffusion of momentum and thermal diffusion for the diffusion of heat. And when the Rayleigh number exceeds a critical value, then convection occurs. And what I'm going to talk about today is looking at trying to look at convection in a regime that's turbulent, so the Rayleigh number much exceeds the critical Rayleigh number for the onset of convection. So this model you can study in a simple way using a standard by perturbing about the conduction profile, and you can use a standard non-dimensionalization using the thermal timescale h squared over kappa as the timescale and the distance between the plates as the unit of length. And if you do that, you obtain these equations that I've written down here. So in the Boussinesq approximation, we have an incompressible fluid where the only effects of density variations are accounted for in the buoyancy term, which when we've non-dimensionalized in this way appears in the term RAPR theta in the z hat direction, which is the buoyancy force on the right-hand side of the momentum equation. And with this non-dimensionalization, there are three non-dimensional parameters if you have rotation in there. So one of them is the Rayleigh number that I've just mentioned. One of them is the Prandtl number, the ratio of viscosity to thermal diffusivity. And the other parameter is, which appears in the Coriolis term, the one on the last one on the, in the first equation, the last term on the left-hand side. And this involves the Ekman number, which is the ratio of viscosity to viscous forces to Coriolis forces. So we only need three dimensionless parameters in this problem to determine what happens in rotating convection. So what I'm going to do in this talk is actually use a different way of representing the problem that doesn't use the same non-dimensional numbers to try and simplify the presentation. And so I'm going to go back to what looks like the dimensional equations, or as I've said, T is actually a buoyancy variable. So I've essentially combined alpha and G with the temperature variable to define that. And these are the Boussinesq equations that I'll mainly be talking about. So the reason for not using the standard non-dimensionalization will become clear when I discuss the theories that I'll discuss later on. But everything that I'm going to discuss can be referred to in terms of the standard non-dimensionalization as well. And I'll do that at various points in the talk. So we've got the standard momentum equation for a Boussinesq fluid and the heat equation perturbing about the conduction profile and also incompressibility, which is consistent with the Boussinesq approximation, which is valid in stars and planets if you're looking at length scales that are much smaller than the density and pressure scale heights, and for velocities that are much less than the sound speed. So this might be thought to be valid somewhere deep in a convection zone of a star or planet that's not near the surface. But for our purposes, what we want to do is to look at convection in this model and to try and understand the influence of rotation, particularly in turbulent convection. So to avoid, to simplify presentation of the physics, I am going to avoid using the Rayleigh number, Prandtl number, and Ekman number as much as I can, but I will come back to that in a few points. The reason for that is I'm mainly going to be looking at verifying diffusion-free scaling laws, and it helps to use input parameters that are not dependent on the diffusivities to do that, and similarly for the analysis. So I'll illustrate hopefully why when I discuss this later on. So in simulations, we do non-dimensionalize things because we're not, none of us are engineers, so we're going to use non-dimensional numbers. We'll use the layer depth h as the length scale, and we're going to define a time scale based on the heat flux or buoyancy flux through the domain, which you can calculate as h to the 2/3 over f to the 1/3. So I'll come back to this point, but essentially we're going to run simulations in which the length scales are 1 in the z direction, and in which the heat flux is 1 as well. So this model so far is only studying the polar regions of a planet or star, so I'll initially focus on studying the influence of rotation on convection in this model, and then I'll move to general latitudes. So if you don't have rotation, then it turns out that you can just use dimensional analysis to determine how the convective velocities and temperature gradients depend on the input parameters. And that's because in this case, there is only one time scale, so it's the one I mentioned here, h to the 2/3 over f to the 1/3 is the only time scale in the problem if you have no rotation, and if you ignore diffusion processes, and h is going to be the layer depth. So in terms of these two parameters, you can actually determine how the convective velocities must scale in this diffusion-free regime, and the scale as given in the red box here, f to the 1/3, h to the minus 1/3. And similarly, you can determine what the mid-layer temperature gradient is in convection, so what the temperature gradient needs to be to transport a given flux. And this you can get purely on dimensional arguments. So I'm actually going to discuss a heuristic derivation in a different way, because it's going to relate more to what we do in the case with rotation. So when you add rotation into the problem, there is more than one time scale, and so you can't just determine these scalings purely based on dimensional arguments. So the idea is we're going to think of a picture of convection in which we have a turbulent steady state that's in a statistically steady state, where we have a sea of modes which are individually well described by linear theory, but in which the amplitudes of these modes are determined by the nonlinear terms through the criterion that the growth rate of each convective mode, the linear growth rate, must balance a nonlinear cascade rate. And so this is going to be, sorry.
Maybe I'll ask a question.
Yeah, sure.
So here you are taking the boundary condition as constant heat flux boundary condition rather than constant temperature boundary condition, or not clear?
So yeah, you're right, we will do that. So that's a good point. So I'm trying to not be explicit about the boundary conditions before discussing the model. So what I'm discussing here is, I guess, general if you fix the heat flux. But in the simulation, that means that instead of having the fixed temperature boundaries, we don't constrain the heat flux in the interior. What we're going to do is actually fix the flux. That's right. Okay. So I'll discuss that in, I think, 2 slides' time. I'll show the model. And yeah, we're going to fix the heat flux through the domain rather than the temperature difference.
Excellent. Thank you.
So we're thinking of a simple picture of convection is where we have a sea of convective modes where the amplitude of these is determined by the criterion that the growth rate balances a nonlinear cascade rate. And we know that the growth rates of convective modes are going to scale with the magnitude of the buoyancy frequency, which is, so I've said n squared is negative, so the n is imaginary, but what I mean is the magnitude of the growth rate of the convective modes scales with n. And in non-rotating cases, the length scales in the horizontal and vertical directions are comparable, and so the u dot grad u, in terms of the dimensions of it, is going to scale like ku times u, and so we can get a cascade rate ku, then balancing a growth rate is like saying n is of order ku. So this is the effects of nonlinear terms in this model. So we can use the linear equations to determine the heat flux due to convection. If we assume the convective flux is much larger than the conductive flux, then the heat flux is just given by the product of the vertical velocity uz and the temperature. And we can average that over the xy plane. And if there's a good correlation between rising warm fluid and falling cool fluid, then we can take the product of the RMS velocity fluctuations and temperature fluctuations to well represent this average of the product. And we can use the linearized temperature equation to determine that temperature fluctuations must scale as n times uz. So we can get that just from the temperature equation on the previous slide, ignoring the diffusion processes, just by balancing the d by dt term with the minus n squared uz term on the right-hand side. So in magnitude, That's saying that essentially temperature is advected vertically for a cascade time, and the implication of that is that the thermal fluctuations are of order NUZ. In non-rotating cases, we can do this more rigorously, but we can show that the modes that transport the most heat have similar horizontal and vertical length scales, so within an order 1 factor, and they're comparable with the size h, the size of the domain. And on those length scales, the dominant modes have vertical and horizontal velocity components that are comparable. So we can do this more rigorously, but if you just use this heuristic derivation, you can combine these arguments to get the same mixing length scalings given at the bottom. And there isn't an advantage to doing this in beyond dimensional analysis without rotation, but there is when we include the rotation in this problem. So this is mixing length theory for Boussinesq convection. It differs from mixing length theory in stars because h in stars is really the pressure scale height or the density scale height, usually the pressure scale height. Whereas in our model, we don't have any, well, essentially the only length scale in the problem is the box size. So this is mixing length theory for Boussinesq convection. And in the rotating case, we can actually apply the same arguments with one change. The only change is that rotation tends to inhibit variation along the rotation axis, and it prefers the excitation of modes that take the form of tall, thin columns in the form of rapid rotation. So if the rotation is rapid, such that the rotation rate omega is much larger than the magnitude of the buoyancy frequency, then in that limit, convection does take the form of tall, thin columns. And in linear theory without diffusion, the length scale in which the smallest wave number in which the convection occurs is comparable with this length scale that I've referred to as k omega in the middle of the slide here, which is 2 omega over n times kz, the vertical wave number. And this length scale in the limit when omega is much bigger than n is much larger than the vertical wave number. And so this means that the horizontal length scales are much smaller than the vertical ones. So in rapidly rotating convection, convection takes the form of tall, thin columns. And that's the only change we really need to do to the mixing length arguments to derive an equivalent mixing length theory for rotating convection. And so we can use exactly the same arguments, except that the nonlinear term u grad u is going to be dominated by the horizontal variation, the horizontal length scale k perp, which is then much smaller than the vertical one, so the horizontal wave number is larger. And in this limit, the modes that transport the most heat, we can show actually have wave numbers comparable with just a bit larger than this onset wavelength, k omega, which is the onset wavelength is perhaps per terminology, which is the smallest wave number on which the linear modes grow in the absence of diffusion. And if you combine these arguments in the rotating case, they're otherwise the same as in the non-rotating one, we get these scalings in the bottom left. So these are scalings for the vertical velocity as a function of the imposed heat flux, the depth of the domain, and the imposed rotation rate. And similarly, we've got scaling for the temperature gradient required to transport the same flux. So note that this is a positive power of the rotation rate, indicating that rotation tends to inhibit convection, and it requires a larger temperature gradient to drive the same, to transport the same heat flux. And similarly, we can show that we can have that the wave numbers then scale with omega to the 3/5 in this scaling as well. So these are dimensional scalings. They don't involve diffusivities, and so this is a rotating mixing length theory, which describes the dynamics of rotating convection that's very turbulent when the diffusivities are unimportant. Well, I'll show you that it is. The idea is that this is meant to apply in that regime, and what we need to do is test this in simulations. So this theory was first proposed by Dave Stevenson in 1979. Some of the ideas actually slightly predate that. There's Flazar and Girash has a paper in the previous year that has many of the same ideas, but they weren't quite as fully developed. And there's even a paper by Raymond Hyde in 74 that derived the same velocity scaling here, but didn't derive the other scalings. And it turns out these arguments have been rederived by many people in the literature and discovered in different ways. There was Ingersoll and Pollard, Aubert et al., and Gillett and Jones, and a nice treatise in geophysics by Chris Jones in 2007 that discusses this as well. So these arguments are not new. They were discovered in the 1970s, but certain aspects of these haven't been conclusively tested in simulations. particularly in cases away from the poles, which I'll extend the theory to discuss later on. So note that this theory cannot be obtained purely on dimensional grounds. We need to go beyond that and add in other ingredients to obtain this. So I'm going to discuss simulations with two different setups. The first setup is simulations of fixed flux Rayleigh-Bernard convection. I'll write down the boundary conditions on the next slide. So we're going to solve the equations at the top right. And those simulations that have fixed flux Rayleigh-Bernard convection have been solved using the Idealised code, and that's setup A. In setup B, we're going to have a setup that's quite similar to Rayleigh-Bernard convection, but we drive the convection through internal heating and cooling layers. So we still have boundary conditions that fix the flux through the boundaries to be 0, but we impose a heat flux in our units of 1 through the interior by having a heating layer near the bottom boundary and a cooling layer near the upper boundary with an equal magnitude, such that the integrated heating rate would give you a heat flux through any horizontal plane of 1. So we non-dimensionalize using the layer depth h and this timescale based on the flux, so that f is 1 and h is 1. And the reason we do that, well, hopefully is clear from the previous slide, is that if they're fixed to be 1, then the only parameter except for the diffusivities and the box size involved in this problem is omega. And so it allows us to neatly obtain comparisons with the mixing length theory. And so that's why we developed this non-dimensionalization. It's simpler to test the diffusion-free scalings than if we were to use Rayleigh number, Ekman number, and so on, where to vary the viscosity separately from the rotation rate means changing both of those. But the idea is essentially, it can be done obviously using the standard equations as well. So we're going to use stress-free boundary conditions for the velocity at the top and bottom, and impermeable, periodic in the horizontal, and in the polar cases we vary the perpendicular, the box size in the horizontal direction so that the bulk properties are independent of this parameter, so that we've captured the modes that transport the most heat, using intuition from both linear theory and nonlinear simulations. So the numerical methods, as I've said, the Idealised code, which is a Cartesian pseudospectral code, is used for some of these simulations. This uses a Fourier spectral method in the horizontal and Chebyshev in the vertical. So the simulations using that code were done by Laura Curry, I think is actually in the audience. And these use a second order time-stepping scheme, mixed, implicit, explicit, where we fix the thermal boundary conditions to be 0 temperature at one boundary and fixing the heat flux to be 1 at the other boundary. So in a steady state, we have a heat flux of 1 through the domain. And in setup B, we use a spectral element method with a second order characteristics-based time stepper for the nonlinear terms and an implicit backward difference formula for the diffusion terms. And we use thermal boundary conditions that have the flux being 0 through the boundaries, fixing the temperature at one boundary, the flux at the other, so that all of the heat flux is driven through the heating and cooling layers, through the bulk of the fluid. The advantage of using the heating and cooling layers is that it thickens the boundary layers, and it means that you can often get away with lower vertical resolutions than in Rayleigh-Bernard convection, where the boundary layers can be very thin in weakly rotating cases. And the advantage of studying both of these is that we can see whether these scaling laws are valid in different ways in which convection is driven, so how sensitive they are to how you drive the convection. So what are the results? So I'm initially going to talk about the polar case, which we published back in 2014.
I'll ask you a question now.
Yes.
So you vary viscosity, right? Prandtl number is 1, but you very new and
that's right.
So the Reynolds number, Reynolds number is another parameter for you, right? 1 by nu.
So nu and kappa are also parameters in the model, and that's right.
So nu and omega, these are the two parameters for your simulations.
So in all of our simulations, so I haven't been explicit on this slide, but I should have been, we use Prandtl number of 1 for the simulations.
Yes.
So that means the viscosity and thermal diffusivity are equal. So the parameters in the simulation that are physical ones is purely the rotation rate and the viscosity.
Viscosity.
Yeah, that's right. So it's equivalent to using a Rayleigh number and an Ekman number, but for the purposes of testing these scaling laws, we intentionally didn't use that, so we could view these more simply.
Excellent. What's the Reynolds number, by the way?
Good question. I can probably tell you that at the end when I look at the outputs, but
okay,
I'll show you some velocities as well, and you can see whether you... I can tell you that, shortly. It depends on the simulation, actually.
Excellent. Okay.
So we vary the viscosity a lot, because what we want to do, we also vary the horizontal length scale quite significantly. because we want to capture the dominant convective modes, but when you go to rapid rotation, the box size becomes very thin, and it's very thin and tall. So what we need to do is vary the viscosity so that we try to keep a reasonably supercritical convection, and essentially it means we decrease it as we increase the rotation rate.
Excellent. Okay, thank you.
I'll try and be a bit more precise about that, but when I go through this.
Sure.
So qualitatively, what happens in the convection, this is showing the case at the poles, as I've discussed so far, showing the average temperature profile averaged over the XY plane as a function of Z in the statistically steady turbulent state. And this is using a heating cooling simulation. And you can see here that as you increase the rotation rate, the temperature gradient in the bulk is increased. So this does indicate, at least qualitatively by eye, that the idea of the theory is correct in the sense that it does predict that the convection is inhibited. To transport the same heat flux, you need a larger temperature gradient as you increase the rotation. So this is just qualitatively to show you this is what happens as you increase the rotation rate. So the shading just indicates the fluctuations around the mean. And these are for different viscosities. So I'll indicate a little bit why we do need to vary that. So just to give you a very qualitative validation of the theory, we can plot, this is what the flow looks like. It's showing the vertical velocity in the simulation with the parameters at the bottom. So the viscosity and thermal diffusivity are indicated. So from this, we can determine the Reynolds number if you look at the numbers in the UZ and compare it to the viscosity that's used there. So depending on how you want to define that and what length scale you want to use, you can use one based on the global length scale H quite easily based on these parameters. So on the left, I've just shown a simulation with omega of 10, so this is into the rapidly rotating regime. And you can see here the convective motions indicating the vertical velocity, with both the red is the rising fluid, the blue is the falling fluid. And so the red, if you correlate it with temperature, that's the rising hot fluid, and the blue is the cooling, the cool downward propagating fluid. And on the right is a simulation with 100 times larger rotation rate. Now we need to decrease the box size in the horizontal to capture the dominant convective modes in an efficient simulation that's computationally accessible. So we use a much thinner box, which has a horizontal length scale of 0.05 relative to the vertical one. So what I've done to illustrate whether these scaling laws are valid qualitatively is I've scaled the velocities using the color bar from the left panel to the right one by the amount that you predict from the theory. So 100 to the minus the fifth is the 100 is the ratio of the two rotation rates, and minus the fifth is the scaling predicted by the velocity scaling from the theory. And so if the theory is correct, you'd expect the colors to be similar in both of them once you make this rescaling of the color bar. And similarly, we can rescale the structures on the right and multiply them by a factor of 100 to the 3/5. And you should see that the convective structures look very similar in scale in the horizontal than they do in the left panel. So the box size is strictly not an exact multiple of this, but you can see that the structures that have been multiplied by this factor have a similar scale as they do in the left panel. So 100 to the 3/5 is a scaling for the length scale and how that should scale as you vary the rotation rate. So you can see, at least qualitatively, that this isn't completely wrong, in that it seems to give you roughly the right convective velocities as you vary the rotation rate in this regime, and also the right horizontal length scales as well, that are well described by the theory. But so far, this isn't very quantitative, so obviously you want to go beyond that. So we can look at scaling laws for how the properties depend on rotation rate in this model. So remember, we're fixing F and we're fixing H, so the only parameter that it isn't the diffusivities and the box size is omega in this model. And this is showing the temperature gradient in a steady state, and it's showing simulations for 3 different diffusivities, so the points in L, M, and H. And there's actually 2 different codes in here, but for this setup, they're all the same setup, actually. They're not different. We don't use the Idealised simulations for this. It was actually a different code using a sine-cosine decomposition, the Snoopy code that was used for most of these symbols. So the theoretical prediction is given by the 4/5 slope, and we can see that that seems to work well to describe the mid-layer temperature gradient in the simulations. So we fit the the temperature gradient in the middle 1/3 of the domain, find out what the slope is, and then plot that as a function of omega. And that's what's being shown here. So the theory seems to work quite well at describing the scaling of the temperature gradient, the mid-layer temperature gradient in steady state. And as far as we're able to vary this, we varied the viscosity by, in these simulations, not by a huge factor, some of them by a factor of 2, some by a factor of 10 or so between these different points. And we don't see any obvious difference. And so while we haven't done a wide parameter survey varying the viscosity for these simulations, it does seem as if these values are not strongly affected by the diffusion coefficients, as you'd expect if the theory is approximately correct. And this is equivalent to what's been obtained in, you can write this also in terms of Nusselt numbers and Rayleigh numbers, and it's equivalent to a result that's been obtained using an asymptotically reduced model that's valid in the limit of rapid rotation by Keith Julian and collaborators, and later shown in some nice numerical simulations by Stefan Stelmach of standard rotating Rayleigh-Benard convection, where they obtained that the Nusselt number goes as this one to the right. I need to minimize my own face to the right to be able to actually see what that is. It's, so I'll have to minimize my own face at the right so I can actually see this. Nice, there we go. Good. So it's Rayleigh number to the 3/2 and E Ekman number squared. So in that format, it's not obvious that the heat flux is independent of the diffusivities, but it turns out when you rescale all the parameters in that it's equivalent to what I've shown you at the top left. So it is really a diffusion-free scaling law. You can also write it more directly from what we've got in terms of a flux Rayleigh number, which is related to the Rayleigh number I mentioned previously, except that it involves the flux rather than the temperature difference between the plates. And you can write that in that form at the bottom as well. So I hope that this illustrates that why we're using the dimensionless numbers that we are rather than the standard ones, because if you're trying to test scaling laws that look like that, it's much more less obvious that they're diffusion-free in that form than it is if you write them using the notation that we've used. But it is equivalent to results that have been found in the literature. We can also test the other scaling laws here. So we can test the scaling law for the temperature fluctuation and the convective velocity. As this I referred to as UZ on the previous slide. And both of these have a rotation rate dependence, which is well explained, well matched by the simulations. So the convective velocities decrease as we increase the rotation rate, indicating that the convection is being inhibited by the rotation, and the temperature fluctuations are larger as we increase the rotation rate. And the final scaling law, which I'll revisit again later on, is we can also look at the wave number that dominates the heat flux. You can kind of think of that as a centroid wave number for the heat flux, using the heat flux spectrum, which is the Fourier transform of UZ multiplied by temperature, convex conjugate of the temperature field. And we can calculate a k hat, which is this wave number that dominates the heat flux, using the formula in the bottom left. And you can see from a range of simulations here that seems to follow a scaling that matches a 3/5 prediction of the theory. Now, there are some subtleties about this that I'll come back to later on, in that if you plotted it in terms of the onset scaling, you might think that it's more related to that, but I'll illustrate why we believe this is the relevant scaling later on. And this scaling does differ from what you predict if you believe that diffusivities are important in determining the length scale. So near the onset of convection, including diffusion, including viscosity and thermal diffusion, you'd have a length scale for the convective modes that's given by this in the top right, which depends on the Ekman number. And what we're claiming here is that's not the relevant length scale. And the relevant length scale instead is determined by a diffusion-free mixing length balance that I've mentioned already. And there's some support for this in spherical simulations as well, of convection by Tomaga Steen et al. And Celine Gavilli's simulations as well, if you make the extrapolation to the spherical problem for the results I've discussed. So to summarize this particular piece of work, before I move on to the tilted case with misaligned gravity and rotation, a very simple mixing length theory, rotating mixing length theory, predicts the scalings of bulk properties in rapidly rotating convection when you have aligned gravity and rotation. And it works well in the regime of small diffusivities. and each of the predictions have been validated numerically using simulations. So the scalings of this theory have been rediscovered and rederived in many different ways and by others since then, since Stevenson. But some of them haven't been as well tested, which is why we revisited this in our 2014 paper. And it's also been referred to as the inertial theory of rotating convection and as CIA triple balance to make things more confusing, depending on which community you're coming from. But it's all equivalent to rotating mixing length theory when you're discussing the same model, so plane layer convection. So one thing I've ignored discussing here is the influence of large-scale vortices, which can be formed in rotating convection, which can form and grow in rotating convection. Partly the reason for that is that these are unlikely to modify the scalings much from what we've observed, but we do have these in some simulations, but they don't tend to actually change the scaling law from these rotating mixing length theory results. But further work should look at these in more detail. So the next thing I'll move on to looking at is looking at non-polar latitudes. So in this case, we're going to define a latitude angle, which is 0 at the equator, 90 degrees at the poles, and look at an arbitrary latitude and see whether we can develop similar scaling laws for the heat transport in this case as well. So we're going to build up on some old papers by Hathaway and Somerville in the 1980s that looked at this setup for standard Rayleigh-Benard convection, but we're able to look at much more rapid rotation and smaller diffusivities, and we also fix the flux rather than the temperature difference across the domain for the reasons that I've already mentioned. So in Stevenson's paper, he proposed that the same theory applies if we simply replace the rotation rate with the vertical component of the rotation vector, omega sine phi. So we found this doesn't work as well, so we've developed an alternative extension to rotating mixing length theory, which develops on Stevenson's theory that works at non-polar latitudes. So I'll discuss that in the next few slides. So the aim of this work that we began about 5 or 6 years ago and published in a paper last year was to develop a theory and test these new scalings as a function of the angle phi using a wide parameter survey of simulations using the two different setups that I mentioned. So the coordinates I'm using, x is the zonal direction, azimuthal direction, y is the meridional direction, and z is the radial direction in the box. So it's like I'm looking at these tilted Cartesian boxes in this section, where the rotation axis is tilted relative to z. So I can derive rotating mixing length theory in a different way, and this is what we did in a recent paper, just to make the assumptions more explicit. So what we can do is write down the linear equations for convective modes without diffusion, which are given by the equations in the top right. So here I've just used n star to remove the minus sign from n squared previously, but this is equal to minus n squared, and is the temperature gradient in the conduction profile. So these are the linearized equations, and what we're assuming really is that convection consists of a sea of linear modes where the amplitude is limited by the growth rate balancing a nonlinear cascade rate. And we need two aspects of the theory. So one is a relation between the heat flux and the convective velocities, and one is a relation between the growth rate and the convective velocities. And from that, we can determine a theory that will be equivalent to what I mentioned previously when analyzed in the right way. So if you're looking at tilted convection, and in the absence of rotation, we just have impenetrable boundaries on z equals 0 and 1. And we can seek modes which have the form of plane waves in x and y, but have kind of a tilted wave-like structure, accounting for the fact that modes preferentially occur in the limit of rapid rotation. Modes are preferentially aligned with the rotation axis, the flows are. And so it turns out we need to study modes which have the structure given here, so that the exponential factor with the minus ky tau z term is non-obvious, but is needed to capture the tilting of the rotation axis. So we can look for linear modes of that form. They satisfy the governing equations, and we obtain the dispersion relation, which is this quartic, which I've given here. So this was done in Hathaway's paper as well as in Stevenson's. So this is just linear theory, the linear growth rate of the convective modes. And if we have a single linear mode, we can determine the heat flux transported by that mode as just the product of the vertical velocity times the temperature. And we can obtain an exact result for this for a single mode by multiplying by the momentum equation by the velocity of a single mode, and horizontally averaging, and we get this result that the heat flux is equal to sigma times the horizontal average of u squared, where u is the velocity of a given mode. And we're going to use that to construct a theory by then relating the we also use the argument that we relate the growth rate of a convective mode to its nonlinear cascade rate to determine the amplitude of a mode. So the idea is if a mode has a larger amplitude, then the nonlinear cascade rate will be larger. And so to get a mode in steady state, then we need this balance to hold, essentially. So this is going to limit the amplitudes of modes. And we're going to consider flux due to essentially all the modes with a given characteristic length scale of order 1 over k. And based on this exact result, we can get that this must scale, f of lambda, this quantity must scale as the growth rate times u lambda squared, where u is the typical velocity scale of modes with a given length scale. And we can relate then the growth rate with the wave number times u of lambda, and we can get this relation at the bottom then, that f of lambda must scale, if these arguments are correct, with the growth rate cubed over k squared. And this is something which does incorporate the anisotropy when you have a tilted rotation vector, because sigma is just is a function of kx and ky, as well as the vertical wave number. So this gives a scaling for the heat flux of a given mode. And so if we want to calculate the heat flux due to all the modes, then we need to take the weighted sum of them all and sum up over all of the modes. And so what we do to derive a more rigorous version, well, a more general version of the mixing length theory that we derived heuristically previously, is to essentially use this argument where we define f of lambda to be equal to some constant times sigma cubed over k squared, where if the theory is valid at all, then it needs to be predictive. So for one constant value of a, it needs to predict the variation in the bulk properties as a function of omega and phi and other parameters. So what we do is we fit the value of a in the simulations to fit simulations at the pole with a given value of the rotation rate, and we use this theory to then predict the evolution of other quantities. So we do this numerically as a proof of concept, but you can actually show where the previous theory comes from by, if you differentiate f of lambda and determine which mode maximizes the heat flux, you get exactly the same rotating mixing length theory we had before. And that gives the scalings given at the bottom right. So if you just think of one mode dominating, then you get the mixing length theory given at the bottom right, with the exception that omega is replaced by the vertical component of omega. So this theory was proposed by Stevenson to apply a general latitude. But it turns out that we found that we need to take into account the anisotropy of the modes in k-space and actually calculate the sum due to all of the modes rather than just the single mode that maximizes the flux. And I'll show you why that is in the next few slides. So the assumptions that the theory makes is that the convection consists of a sea of uncorrelated linear modes, described by linear theory without diffusion, where the amplitude of each mode is determined by balancing the linear growth rate with a nonlinear cascade rate. And this theory incorporates both slowly non-rotating convection as well as the rapidly rotating limit. And in principle, if it's valid, works for arbitrary phi as well. So what we're going to do now is test it in simulations. So what happens in tilted convection? So this is showing an example with an angle of 45 degrees for the latitude. And what you see for the temperature is plotted in the top panel, I think the temperature fluctuation, and in the bottom panel, the vertical velocity. And we can see that the structures are aligned along the rotation axis in the YZ plane. So the convective motions like to orientate themselves along the rotation axis, and the plumes, you can see, are oriented in that direction. And this is an important difference between an important aspect that occurs in tilted rotating convection in terms of the flow. In these simulations, there are no spatially averaged mean flows that develop except near the boundaries, as shown in the bottom panels. But I'll come back to the importance of spatially varying horizontal flows, because we do get spatially varying zonal flows which are aligned with the rotation axis in these simulations, and they can strongly affect the properties of convection. So first of all, we can look at 4 different latitudes here for the same. So we do vary the diffusion coefficients for each of these to keep the system roughly similarly supercritical as we vary the rotation rate. So I haven't specified the numbers here because it would make this figure too complicated, but I'm plotting the temperature, mid-layer temperature gradient as a function of the rotation rate for various different latitudes. So 575 degrees is close to the poles and 530 is closer to the equator. And the first thing you can see is that at each latitude, the mixing length theory prediction that the temperature gradient scales as omega to the 4/5 also holds, even at different latitudes. So there are a few outliers here, which we believe is due to zonal flows, but most of the points are consistent with the same omega to the 4/5 scaling applying in the tilted cases as well. We've also made a prediction from the multi-mode theory, which we do numerically by integrating the spectrum of modes, which is given by the black line here, which is only fit for one simulation at the poles for one given value of the constant A that I mentioned previously, and that gives the solid lines. And we've done a similar thing with the single mode theory, just by fitting the scaling laws at the poles. And it's not as clear in this panel as it is in the next slide, but you can see here that the theory does seem to be predictive in the sense that it seems to approximately predict the variation with latitude quite well. At least the multi-mode theory does, when we take into account the contribution of all of the modes in the spectrum, which is the black line here. And these results have been found actually with similar results have been found with both setups. So the fact that the rotation rate scales as omega to the 4/5 at each latitude is consistent with global simulations that have found results similar to what I mentioned before at the poles, which are spherical simulations where different latitudes would obviously be included in those simulations. So this is perhaps probing one aspect of why that is in their simulations. So we can plot similar things for two different rotation rates using both setups as a function of the latitude angle, which I've done in these panels here, now showing how things vary as a function of the latitude angle. Now in this model, the solid line is the prediction of the multi-mode mixing length theory, and the thin dashed line is the prediction of the single mode theory, where we just incorporate the vertical component of the rotation vector to account for the effects of rotation. So we can see here that the theory, there are some outliers that I'll come to explain, but the theory works reasonably well to explain the latitude dependence of the heat transport. So in the absence of zonal flows, convection becomes more efficient as we approach the equator, in that you need a smaller temperature gradient to drive the same heat flux. And that's really just due to the, it's related to the rotation inhibition of convection and the Taylor-Proudman effect. So it's related to the fact that omega z becomes smaller as you move toward the equator. But one thing that you can see here is some points are outliers, the ones with the light grey line, or light grey symbols, and these are ones in which zonal flows are strong. So I'll illustrate these in a couple of slides' time. So you can also see that we have varied the viscosity in some of these cases to show that we really have reached a diffusion-free scaling. So I've chosen one example in the top panel, and this is showing quite a large variation in the viscosity in the simulation with Prandtl number of 1, where we varied it from 10 to the minus 2.5 to 10 to the minus 4. And there's initially a change due to varying the viscosity, but then we reach a regime in which the temperature gradients are not strongly affected by diffusion processes. So it is consistent with the diffusion-free scalings being valid in that regime. If you prefer to see things interpreted in terms of the usual non-dimensional numbers, then I've just illustrated in the middle panel here that the Nusselt number scales as the flux Rayleigh number to the 3/5. So that's just using the standard non-dimensional numbers. So you can convert our units to the standard non-dimensional numbers straightforwardly, and it's consistent with what other groups have found. We can also look at how the velocities scale with latitude. It turns out the convective velocities don't vary much with latitude until you get close to the equator. These are the RMS convective velocities at the mid layer in the simulation. But the convection becomes slightly faster as we go toward the equator. And we've also looked at the thermal fluctuations, which match the theory a bit less well, but we think the reason for this is zonal flows. So I've now got, so I'll discuss the zonal flows and then come back to this point actually. So one thing these simulations do observe is the formation of spatially varying mean zonal flows. So the zonal flows are illustrated in the left panels here and meridional flows are illustrated in the right panel. And the zonal flows are flows which are they're varying in y, but they're independent of x. And these are flows which are oriented with the rotation axis. So you can see then that these plots of ux, where these flows are essentially constant along the rotation axis. So these really are zonal flows. And the strength of these is they can be very strong, but it depends on the box sizes in the box as to how strong these flows are. And they tend to be stronger if the box is narrower, thinner in the x direction than in the y direction, and weaker if you extend the box in the x direction versus the y direction. I think this is related to parasitic shear instabilities that can act on these zonal flows. But the key point is that these simulations do have strong zonal flows, and the properties of these flows depends on the numerical parameters, such as the box aspect ratio. And so it's hard to extrapolate these directly to astrophysics and geophysics, because in reality, in a spherical problem, we'd have other effects that would come in to affect these zonal flows. But in these simulations, we can control the strength of these flows by controlling the box size. And what we found is that the previous theory works well in cases when the zonal flows are weak, but cases when they're strong are given by these grey points, and that's where we have quite a departure from the theory. And we can show that zonal flows inhibit the convection. So this has got a complicated plot. So if you just concentrate on the top left plot, that's the only one that I'll discuss. This is showing the zonal velocity, the RMS zonal velocity, as a function of the mid-layer temperature gradient in a range of simulations with different box sizes. And the only point I want you to get from this is that there is a positive correlation between the temperature gradient and the zonal flow velocity. And our interpretation of this is that the zonal flows inhibit the convection and require the convection require you to have a steeper temperature gradient to drive the same heat flux. So this really is an example of zonal flows inhibiting the convection in these simulations. And this can explain why we have some departure from the theory at non-polar latitudes. And we can show that it really is the zonal flows rather than any meridional flow that's relevant by plotting the mid-layer temperature gradient as a function of this anisotropy parameter, which is 1 if, so it's 1 if the zonal flow dominates, and I guess, -1, I guess, you can be negative, I guess, if the meridional flow dominates. And you can see from this that there is a strong positive correlation here, indicating that the temperature gradient is larger in cases when you have strong zonal flows. And this is indicating that zonal flows inhibit convection, but that meridional flows don't play as much of a role. Partly strong meridional flows are not observed in our simulations, and partly they don't play as strong a role at inhibiting the convection as the zonal flows. So zonal flows can be important here, and they're not incorporated in the theory. So we've intentionally looked at comparing the theory with cases where we expect it to work when the zonal flows are weak, and it seems in that case to work quite well. So the final quantity I wanted to mention in these simulations is we've looked in more detail at the wave number that dominates the heat transport. And so we've again calculated it based on this centroid wave number, K-per multiplied by the heat flux spectrum, the integral of that. And that's given by the symbols in both setups for simulations with a given rotation rate of that we chose to be 10. And the black line here, well, the dashed line actually is the one that is the prediction of the single mode mixing length theory, where we have an exact expression given on the left, which you can determine analytically for the wave number that dominates the heat transport. And it seems like that works very well. And note that there are actually no fitting parameters here. So, well, there's indirectly a fitting parameter because the n star, which is the temperature gradient, is determined through the single fitting parameter I mentioned previously. But there's no additional fitting parameter in determining this. This is actually a prediction that determines the wave number that dominates the heat transport. And it does match the simulations very well. And this is a diffusion-free scaling, so it doesn't depend on diffusion. So we can also look to see whether the diffusion scaling involving viscosity is relevant, because it's been claimed in many places in the literature that that is the dominant scaling, even in rapidly rotating convection. So what we've done here on this panel is plot for simulations at a given latitude, so 60-degree latitude, the wave number that dominates the heat transport from the simulations as symbols, the crosses. And the red line is the prediction from the theory, again with no additional fitting parameter beyond the temperature gradient. And that works well to describe the variation as a function of omega. We've also plotted on here the onset wave number, which is what you'd have if viscosity was important in determining the length scale. And so that's given by a famous expression in Chandrasekhar's book and in many other places given at the top, where the wave number depends on the Ekman number to the minus 1/3. So it does depend on viscosity as well as the rotation rate. And you can see naively, well, it does seem as if it scales in a similar way as the simulation points, but it is always significantly larger than the, larger wave number, so smaller length scale, than the wave number that dominates in these simulations. And in addition, in the case when we varied the viscosity in the panel here, so the one with omega of about 30, I think it is, where you see that there are two blue points, one on top of the other, the black points don't move much relative to the blue points, even if we vary the viscosity. So this suggests that viscosity really isn't that important in determining the dominant length scale. And to verify this even further, we can actually look at the heat transport spectrum for a given range of simulations at a given latitude with various viscosities. And I've plotted actually K-per multiplied by the heat transport spectrum, because that's essentially the numerator of the expression we're using to calculate the centroid wave number. And except for the smallest viscosities, what you can see here is that the spectrum is essentially unchanged at large scales. You only have a lengthening of the spectrum. So this really does indicate that the heat flux on the dominant scales, the ones that dominate the heat flux, are not affected significantly by diffusion processes. And that, therefore, that the mixing length theory, this key assumption in that the diffusion is not important, is valid in the simulations that we're showing. Of course, it wouldn't be valid if you're very near onset of convection, but if you're turbulent enough so that you have enough of a range of k's in here, then it seems as if it works quite well. I've illustrated on this also the onset wave number and how that varies between the two different end member cases of the viscosity. And it clearly, except for the case on the left, which is quite close to the peak in the spectrum, as you decrease the viscosity to 10 to the minus 4, it clearly doesn't represent the peak of the spectrum. And so viscosity really isn't determining the wave number in our simulations. So I thought I'd just illustrate very briefly why we need to actually consider the multi-mode problem rather than the single mode. And essentially that's because when you have a tilted rotation vector, the heat transport is strongly, is preferentially occurs due to modes that don't vary along the rotation axis. And so in tilted cases, that means that the modes where the horizontal wave number in the y direction in this case, because we've got rotation in the YZ plane, if you're tilted, then it means that the horizontal wave number in the y direction tends to be smaller for the modes that dominate the heat transport than it is in the x direction. And you can see this in the bottom panels here from the heat transport spectrum in the kx, ky plane, averaged over z. I think actually this was just at the midplane. Yes, just at the midplane. So when you're near the poles for the left panel, it's essentially isotropic in the kx, ky plane. But as you move toward the equator, there's a strong anisotropy, and there's a preference for the heat transport being dominated by modes that don't vary along the rotation axis. So they're modes that vary in x and not in y. And this is also predicted by this f of lambda quantity in theory, which isn't exactly analogous to the UZT, but is related. This also predicts similarly that there's an anisotropy in the, basically due to the growth rate of the linear modes as you move toward the equator. And so at the equator, then having just one mode represents the scalings for the convection, because you can have one mode with a given length scale that well represents a circle. But as you move toward the equator, the anisotropy in k-space and the fact that the modes that don't vary along, that have ky of order 0, take up a smaller and smaller fraction of k-space, and they're the ones that dominate, that needs to be accounted for in the theory. And that's why we've gone through the multi-mode theory here, and why we believe there's a difference between, for example, the dashed line, light dashed line, and the solid line prediction here, and why the solid line works better to describe the simulations. So I think I'll summarize there. So the two papers, if you want further details, they're on the archive, but also published in journals, are at the top right. So I presented a simple rotating mixing length theory, which originally was due to Stevenson in '79, with some ideas from Fosauer and Girash in the previous year. And this explains well the bulk properties of rotating Boussinesq convection for aligned gravity and rotation in the limit of small diffusivities that is believed to be important in astrophysics and geophysics. We extended rotating mixing length theory to predict scalings for bulk properties at a general latitude, and we found that each of its predictions have been tested using simulations, and generally we find good agreement between the simulations and the theory, with some strong exceptions, particularly when zonal flows inhibit the convection. This significantly reduces the agreement. So future work should look at developing a theory that can describe the generation of these zonal flows and their effects on the convection. But I'm not certain whether a Cartesian model is the best way to do this, because these flows are strongly affected by the box size. So really, I think we need to turn more to global simulations to look at this. Although it is possible to analyze the interaction in local simulations that are sufficiently targeted as well. So in both of the setups that I discussed, we do get similar results. So it does seem as if how the convection is driven doesn't affect whether it agrees with the theory or not. And I've also illustrated that these convectively generated zonal flows are produced at non-polar latitudes, which inhibit transport relative to the mixing length theory predictions. But their strengths depends strongly on the dimensions of the box, which makes it hard to extrapolate what's going to happen in reality to these flows and their effects on the convection. So I guess there's an open question as to how relevant this is to real stars and planets, which are not Cartesian boxes of convection, which have variations in the Coriolis parameter, the beta effect, and non-Cartesian geometry. But some of these scalings have also been found in global simulations as well, some of the Nusselt-Rayleigh scalings that I mentioned, indicating that the ideas in this theory are likely to carry over to spherical systems as well. So I think I'll stop there. So thanks for listening. And please, I'd be happy to answer any questions that you have.
So, many thanks, Adrian, for a very nice talk.